Just a quick note before our exam on Friday. Based on some of your answers for quiz number 8, I thought it was worthwhile to kind of clarify the main idea about Chapter 16 and the theorems that are in Chapter 16. So, for example, on the quiz was over section 16.3, which is the fundamental theorem for line integrals. You were asked to compute a line integral, basically. So you're given a line integral like this. And certainly one method to compute the line integral is to parameterize the curve and then evaluate according to that, right? The point of the section, however, is that if your vector field happens to be conservative, that is, if your vector field is actually the gradient of a function, then the fundamental theorem says all you have to do is just plug the endpoint into the potential function and subtract the beginning point evaluated the potential function. So this saves a bunch of time. You compute the potential, which usually only takes a few minutes, and then plug in 2 points. And this is really mimicking the fundamental theorem of calculus from Calc 1, which says if you want to integrate a function, you find an antiderivative and plug in the 2 endpoints of the interval. Okay, so that's the point. If you're asked to compute a line integral, you might be able to use this theorem instead of parameterizing the curve and computing the line integral manually. And as we see with the theorems in the rest of the chapter, it's the same sort of story. We haven't done the divergence theorem yet. That's the second to last section. But for exam number 3, we're focusing on these theorems and then all the other sort of ingredients that go along with it, like parametrizing surfaces and surface integrals and stuff. So what Green's theorem says is, for example, if you have a line integral of a vector field with component functions p and q, you have an alternative to computing it. You don't need to parameterize the curve necessarily, especially if the curve comes in like 4 or 5 different pieces that have separate parameterizations and all that. That might be a headache to do that. But if the curve, of course, is closed and lassos a region D, you can instead compute a double integral over that region D. So think of the theorem as like an alternative, sort of like the fundamental theorem of line integrals, for computing a line integral, across a closed curve like this. And the quantity that's being measured by this double integral has something to do with the curl of the vector field, right? So Green's theorem talks about 2-dimensional vector fields, but once we saw in the curl and divergence section, this computation right here was sort of measuring the amount of spiraling in the counterclockwise direction of the field across the region D. And Stokes' theorem is literally saying the same thing, of course. It's just all popped out in 3 dimensions, as I explained in the video. So make sure you kind of understand the relationship between Green and Stokes, and you can explain that in your own words. But look, Stokes' theorem tells me the same thing. If you want to compute a line integral, you don't have to parameterize the curve and do it manually. Instead, you can compute a surface integral. And several of your exercises were phrased in such a way that you're prompted to take advantage of the theorem in that way. So let me show you what I mean. Like in section 16.3, this is exactly like the quiz question. And again, I realize this section isn't on the exam, but the point that I'm trying to drive home is just happens to be true for 16.3 as well. So they're asking you to find the work done, which you know to be a line integral, right? Compute the work done by the vector field along this curve. Well, you don't have to compute this manually, is the point. In 16.3, the whole idea was to check to see if the vector field was conservative, and if it is, find a potential function and just slap in these 2 points, and that gets you the answer. So, I mean, you're not really getting the main idea of the problem if you're just going back and computing the line integral from scratch, okay? So make sure that you're paying attention to what the question is really asking you to do. And then here, it's the same thing with Green's theorem. Use Green's theorem. don't parameterize the curve and compute the line integral manually. If that were the case, this would be back in the line integral section, you know? It's asking you to use Green's theorem. What does that mean? It means use a replacement for this integral. Green's theorem says you can crank out a double integral instead. Give that a try. And then again, with Stokes' theorem, it's the exact same story. You don't have to compute the line integral manually. You can instead compute a surface integral. So that's what's being asked here. And, at the end of the day, that's the power of these theorems. We're saying that a double integral or a surface integral is equal to a particular line integral. In several of the exercises, you were asked to verify that equality. So crank out this double integral, crank out the line integral, and answer for yourself which one of those computations was easier. Okay, so if you have any questions about how to use these theorems, please let me know before Friday. But again, the main point of this entire chapter is to utilize these theorems. So you're often asked to compute a particular integral, but you really want to use a theorem and compute an easier integral to get that quantity, if that makes sense.